Today we're looking at just some more limit examples. So here's this first one. We have a graph of f that has a couple of removable discontinuities and a graph of g that has multiple jump discontinuities. And I need to make that smaller because there's all kinds of questions in this. Okay. So let k be the function defined by k is equal to 4 minus f of x times g of x. Consider x is equal to 2 and x is equal to 4. Determine whether k is continuous at either of these values. Justify your answers using correct limit notation. All right. Why is that flashing in there? That's bizarre. All right. So we know we're going to be, with something that's this complicated, you're going to need to look at the limits from the left and from the right. Okay? So might as well just start with that. So the limit as x goes to 2 from the left of k of x well, let's see what's going on. So f of x, as x approaches 2 from the left, what does f of x approach? Yes. Okay, so it approaches 4. So this is going to be approaching 0, right? Well, let's see what happens with g of x, because if it's 0 times infinity, then we need to look further. That's another indeterminate form. It's another one, like 0 over 0 doesn't tell you anything. 0 times infinity, who wins? Right? So let's look at g of x. It doesn't look like it's going to infinity. As x goes to 2 from the left, that goes to -1. Right? So that's pretty clearly 0. The limit as x goes to 2 from the right of k of x well, the same thing happens on the first part. That's going to be 0 times, as we approach 2 from the right, that approaches 4, but that doesn't much matter. This is still going to be 0. So the limit as x approaches 2 of k of x is indeed 0. Well, let's take a look at what happens at x is equal to 4. Determine whether k is continuous at either of these values. Oh, so I've got the limit now. I need to find out, well, what is k at 4? Which is usually where I start. Sorry, I wasn't fully engaged yet. So k at 4 is going to be equal to, well, that'll be 4 minus 4 is 0 times g at, sorry, I don't know why I'm looking at 4, k at 2. At 2, f is 4, so that first part will be 0 times, at 2, this is 4, so that's equal to 0. Therefore, k is continuous at x is equal to 0, or x is equal to 2. Let's look at what happens at 4, and I'm going to start with what is k of 4. So at 4, f is 3, so that first part will be 4 minus 3, times, at 4, g is equal to 1, So that's 1. All right, so then let's look at the left and the right-hand limits. The limit as x approaches 4 from the left of k of x. As we approach 4, this value approaches 3, so this first part is going to be 1. But what happens as we approach 4 for g of x? As we approach from the left?
Oh, sorry. We're approaching 1.
Right. So this ended up being 1 times 1 is 1. The limit as x approaches 4 from the right of k of x, the first part's still going to be 4 minus 3 is 1. But as we approach 4 from the right, what does g approach?
That is 4.
That's 4. Therefore, the limit as x approaches 4 of k of x does not exist. And, making sure we answer their question, k is not continuous. At x is equal to 4. What kind of a discontinuity would that be? I know you can't see the graph of k, but what kind of a discontinuity is this going to be?
Jump.
Yeah, it's going to be a jump. All right, let's take a look at part B. Values of f of x at selected values of x are given in the table below. Based on the values in the table, what is a reasonable estimate for the limit as x approaches 1 of f of x? What type of discontinuity does f have at x equals 1? So we don't even have to look at the table for this. Actually, we don't have to look at the graph for this. We need to look at the table. The function is undefined at 1. And as we're approaching 1 from the left side, the function values are increasing kind of slowly. Same is true as we go the other direction. They're like, well, I don't know exactly how big it's going to be, but and again, it says a reasonable estimate. If you said that it was 2.9, that would be a reasonable estimate. I'm going to say 3. Right? That's a reasonable estimate. The limit as x approaches 1 of f of x. It's going to be about 3. It might be a little less than that. Heck, it could be a little more than that. I don't know. All I've got is the table. So what type of discontinuity is this at x is equal to 1?
Removable discontinuity.
Yes, a removable discontinuity. And the reason is f of 1 does not exist, but the limit as x approaches 1 of f of x is about 3. It does exist. So that's how you get a removable discontinuity. The limit as we go towards the point exists, but either the function doesn't exist or it's just not equal to that limit. In either case, that's a removable discontinuity. All right. Let's take a look at this one. This is another one that, and I think that's probably true for many of these. I stole them off of AP Central. Here they lead you a little bit just to make sure that, sometimes people don't teach this limit. I don't know why you wouldn't, but they're like, okay, we'll hedge our bets. So it's known that the limit as x approaches 0 of sine of 2x over 2x is equal to 1. So then what is the limit as x approaches 0 of tangent of 2x over 6x secant of 3x? And you're like, what the heck, man? There's all kinds of weird stuff in that. Let's see what we can do with this. So, I said earlier, when I do trig identities and I'm stuck at all, I rewrite everything into terms of sine and cosine. That's exactly what I would do on this. So this is going to be the limit as x goes to 0 of sine of 2x over cosine of 2x over 6x times 1 over cosine of 6x.
Is it 1 over cosine 3x?
3x, thank you. Now, normally I would completely work this out so that I got rid of all the complex fractions, but as theta goes to 0, this part's just going to go to 1, and so I'm not really concerned with cleaning that out entirely. In fact, since this part goes to 1, I can just replace it with 1. So that'll be nice, and then I'll multiply everything by cosine of 2x over cosine 2x. So this will be the limit as x goes to 0 of sine of 2x over 6x times 1. Well, we'd like this to be sine of 2x over 2x, so we just need to factor out a 3. That'll be the limit as x goes to 0 of 1/3 times sine 2x over 2x. So it's 1/3. You didn't have to change the secant part, but I don't know about you, I'm just more comfortable with sine and cosine. I think that's true for most people. All right, page 2. So here we have a piecewise defined function. F of x is x minus 2 quantities squared times sine of x over the absolute value of x minus 2 for x not equal to 2, and it's equal to pi for x is equal to 2. We want the limit as x approaches 2 of f of x. Okay? So if we just try and substitute in 2, we get 0 times sine of 2, which is 0 over 0, not particularly helpful. And we can't cancel right now because this is an absolute value. Okay? So what we're going to need to do is look at, I would actually rewrite this entirely so that I didn't have to have the absolute value part. So if I'm looking at the absolute value of x minus 2, all right, that's an absolute value function that's just been shifted to the left 2 spaces. So to the right of 2, it's just the line y equals x minus, I'm sorry, stupid. It's moved to the right 2 spaces. So that it looks like this. So to the right of 2, this is just the line y equals x minus 2. To the left, it's the opposite of that. It's negative x plus 2. So I think it's helpful to rewrite this as a 3-part piecewise function. So if x is less than 2, this is going to be x minus 2 quantity squared times sine of x. And I'm just going to write it as the opposite of parentheses x minus 2 for x less than 2. It's equal to pi for x is equal to 2. And it's equal to x minus 2 squared sine of x over, if x is bigger than 2, then I just have x minus 2 for x greater than 2. So now, if we look at the limit as x approaches 2 from the left of f of x, one of these x minus 2's is going to cancel, right? Because everywhere except at 2, that's equal to 1. So that'll be 2 minus 2 is 0 times sine of 2, still 0 over negative 1. That's 0. And here, we can simply cancel those, and the limit as x approaches 2 of f of x is going to be 0 times sine of 2, which is also 0. So the limit as x approaches 2 of f of x is 0. Again, what kind of discontinuity is this going to be? Yeah, this is a removable discontinuity. Why? Because f at 2 is equal to pi, but that's not equal to the limit as x approaches 2 of f of x, which is equal to 0. The limit exists, but it's not equal to the value of the function at that point. All right, let's take a look at this example. If g is the function defined by g of x equals cosine x minus sine of x over 1 minus 2 sine squared of x, what is the limit as x approaches pi over 4 of g of x? You're like, well, this doesn't look like fun. But let's do direct substitution first and see what happens. So the limit as x approaches pi over 4, and I just do the numerator and denominator separately. Cosine x minus sine of x. At pi over 2, what is cosine?
Square root of 2 over 2.
Yep. And sine?
Same thing. Mm-hmm.
So that's 0 in the numerator. That's not a problem for us. Let's see what happens in the denominator. It would be nice if it turned out to be a not 0. The limit as x approaches pi over 4 of, I really should put parentheses around those, 1 minus 2 sine squared x is going to be 1 minus 2 times the square root of 2 over 2 squared. Square root of 2 over 2 squared is 2 over 4, which is a half, times 2 is 1. Well, crud. It would have been really nice, wouldn't it? And it's already all in terms of sine and cosine. Well, that's not great. What could we possibly do? Well, we know that sine of x over x as x goes to 0 is 1, but as we go to pi over 4, not so much. So that's not necessarily going to be a helpful thing for us. Anyone have any ideas? I'm actually stalling for time because I don't have any ideas either. I look at that and I go, well, the only thing that occurs to me is maybe there's a trig identity that I don't remember involving 1 minus 2 sine squared x. The other possibility is maybe I could multiply by a conjugate that would be helpful. If I multiply the top and bottom by cosine of x plus sine of x, I'm going to end up with cosine squared minus sine squared on the top. That doesn't seem very helpful. If I multiply by 1 plus 2 sine squared x, oh gosh, that's going to end up being 1 plus 4 sine to the 4th, or minus sine to the 4th x. That doesn't sound good. So at this point, I go over to my notes and go, I hope I worked this out on my notes. Wow. Wouldn't have thought of that immediately. Okay, so this does involve a trig identity, but it is one that you and I both know. I'm going to replace 1 with sine squared plus cosine squared. So g of x is going to be equal to cosine x minus sine x over sine squared x plus cosine squared x minus 2 sine squared x. So g of x is going to be equal to cosine x minus sine x over cosine squared x minus sine squared x. Now I can factor the denominator and cancel, and life is good again. That's going to be cosine x minus sine of x over cosine x minus sine of x times cosine of x plus sine of x. I will warn you about one thing. Do not cancel right now. Because if you cancel that, it's true everywhere except where sine and cosine are the same. If you say that this is equal to 1 over 1 plus cosine of x plus sine of x, you can do it, but you have to put on one other piece. It would be 1 over cosine x plus sine of x, except where sine of x minus cosine of x is equal to 0. That's the only way you can put an equal sign there. All right, so now the limit as x goes to pi over 4 is going to be 1 over square root of 2 over 2 plus the square root of 2 over 2. Which is 1 over 2 square roots of 2 over 2, which is 1 over the square root of 2. Is that really our bell? Man, I am so off today. I apologize greatly that we didn't get through all the examples. I will try and work some of those out sometime during my copious amounts of free time, and put that on a separate video.